Let's do question 4. Question 4 says that a ball of mass 50 gram is thrown vertically downwards with a kinetic energy of 2,704 joules from a point P above the ground as shown below. At the same instant, a second identical ball Y is dropped from a point Q, which is located below point P. Ball Y strikes the ground with a velocity of 19.6 meters per second. Both balls hit the ground at the same time. Ignore the effects of friction and take downward direction as positive. Okay, fine. 4.1 says define the term free fall. Free fall is the motion of an object when the only force acting is gravitational force. The motion of an object when the only force acting is gravitational force. And now we can move to 4.2. So we're taking down as positive, right? We are instructed to do so. Usually take up as positive, but hey. 4.2 says calculate the time taken for ball Y to reach the ground. So let's pay our attention to ball Y. We are told that at the same instant, a second identical ball Y is dropped from a point Q. So if it's dropped, we know fully well that VI is equals to 0 meters per second. And then it goes on to say ball Y strikes the ground with a velocity of 19.6 meters per second. So VF is equals to 19.6 meter per second, right? So we have VF, we have VI, we always have acceleration, and we need delta T, right? The time taken to reach the ground. Now the question you ask yourself, which formula has all these four variables? Clearly, that is VF is equals to VI plus a delta T. What is VF? VF is 19.6. The velocity at which it strikes the ground. What is VI? It was dropped. Every time when a ball is dropped, its velocity initial will be 0, and then plus 9.8 because we're taking downward as positive, multiplied by delta T. So basically, we divided both sides by 9.8. 9.8. So 19.6 divided by 9.8, that is 2. So we have delta T being equals to 2 seconds, right? And then that's it for 4.2. Now 4.3 says calculate the speed with which ball X strikes the ground. So let's take our attention to ball X. For ball X, we are asked to find VF, right? The speed at which it strikes the ground. So that's what we're looking for. We can find VI because we are given the kinetic energy, right? So we are told that EK is equals to 2.704 joules. And then VF is our unknown. We have the acceleration, obviously, because we always do. And then we are told that the ball hits the ground, the two balls hit the ground at the same time, right? So we also have delta T. So obviously here we're going to say VF is equals to VI plus a delta T. But before that, we need to determine VI, right? So how are we going to determine VI? We're going to say that EK is equals to half mv squared. And then we know that EK is 2.704. which is equals to half the mass. The mass is 50 divided by 1,000, right? V squared. So dividing both sides by this expression here, we're gonna get 2.704 divided by half, 50 divided by 1,000. And then now we can take the square root on both sides, right? So there we take a square root. Here we take a square root, and you will end up getting a velocity of 10.4 meter per second. And then we know that it's supposed to be going down, right? And then So now we have our VI, and we can go on and determine VF. So VF is equals to VI plus A delta T. What is VF? Is our unknown, right? But we know now that VI is 10.4. Acceleration is 9,8 because we're taking down is positive, and the time is 2 seconds. So we basically have 10.4 plus 19.6, which is gonna give you 30 meters per second. So where do we go from here? 30 meters per second down what? We are only interested in the speed, so we don't have to give the direction, but it doesn't hurt doing so. 4.4 says on the same set of axes, sketch the velocity time graph for the entire motion of balls X and Y. So we need velocity time graph. So our velocity is on the Y, and then our time, as usual, it's on our X. So we have velocity here in meters per second, and then we have the time in seconds. Let's pay our attention to ball Y first. Ball Y starts at 0 meters per second when it gets dropped, right? And it goes up to 19.6. So for ball Y, how much time does it take? It takes 2 seconds, right? So we can put 2 here. So ball Y ends up here. So now we can have our VT graph for ball Y. The line is supposed to be straight. And then now let's put our attention to ball X. Ball X starts at 10.4, so somewhere here, right? So it's starting at 10.4, that's the VI, and then it goes up to 30 meters per second, so it's ending up somewhere here. So if we would sketch a graph for ball Y, we'd have something like this. The two lines have to be parallel, right? And then yeah, they have to be they have to all be at 2, right? With regards to the time. So that's the VT graph you would get. You would label that this is your X and this is your Y. A hot air balloon is moving upwards at a constant unknown speed. So as soon as I hear constant speed, I know that A equals to 0 meters per second squared. And then 3.1 says, is the hot air balloon in free fall? Choose from yes or no. When an object is in free fall, the only force that is acting is gravitational force. And if gravitational force is the only force that is acting, then we are going to have an acceleration of A equals to 9.8 meters per second squared. And here clearly, A is not equals to 9.8 meters per second squared. It is equals to 0. So the hot air balloon is not in free fall. So you're just going to write no. And then you give your reason by saying that acceleration is not equals to 9.8 meters per second squared. There's other forces acting on the air balloon. And then before 3.2, there's some statement there that is saying when the balloon is 200 meters above the ground, a small stone A is dropped from the balloon. See the diagram above, and yeah, there it is on the left hand side. Another small stone B is dropped 5 seconds later from the balloon, while the balloon is still moving upwards at constant velocity. And then we are told that stone A strikes the ground at a speed of 62.68 meters per second. And then we have 3.2 and then 3.2.1. 3.2.1 says calculate the speed of the hot air balloon. So because stone A is dropped, right? That means that VI of the stone of stone A equals to V of the balloon, because stone A is dropped. When it is dropped and it was on a balloon, because of inertia, its VI will be the same as the V of the balloon, right? And then, so what we're gonna do, we're gonna use stone A to calculate VI of the balloon, because for the balloon, we don't have much information, so we cannot use the balloon. So we're gonna use stone A. And then we know that VF of the stone is equals to 62.68 meters per second. I'm saying that because it is said that stone A strikes the ground at 62.68 meters. And we know that the acceleration is equals to minus 9.8 meters per second. So as soon as I say minus 9.8, I'm taking up as positive, right? And then what we are interested in is VI. So another information we have is the distance it travels from A to the ground, right? That is delta Y equals to minus 200 meters. Again, I'm saying minus 200 because we're taking up as positive. So which formula has VI, VF, A, and delta Y? Because if we can find a formula with these four variables, then we're gonna be able to calculate VI of the balloon. So the formula that has those four variables is VF squared equals to VI squared plus 2A delta Y. What is VF? VF is also minus 62.68 because we're taking up as positive and then the stone is going down, right? And then equals to VI squared, which is our unknown variable, plus 2 multiplied by A. A is minus 9.8 and then delta Y is minus 200. So what we're gonna do, we're gonna make VI squared the subject to the formula. So we are gonna have minus 62.68 squared minus the whole this whole expression here, which is 2 multiplied by minus 9.8 multiplied by minus 200. Everything is equals to VI squared. So let me put this expression in the calculator and see what I get, which is giving me 8.7824 equals to VI squared. So I can take square roots on both sides. I'll get 8.7824 to the power 1 divided by 2, which gives me 2.9635 meters per second. And then 3.2 says the time it takes for stone A to strike the ground. We have VF, we have VI, we want delta T, and then we have A, right? So we can use VF equals to VI plus A delta T. What is VF? VF is minus 62.68. And then what is VI? VI is 2.9635 plus A is minus 9.8 and then everything multiplied by delta T. So we're gonna say minus 62.68 minus 2.9635 equals to minus 9.8 delta T. Divide both sides by 9.8, we get delta T equals to minus 62.68 minus 2.9635, everything divided by minus 9.8. And then if I put that on my calculator, I get, let me just do that real quick. I get 6 delta T equals to 6.69836 seconds, right? So we can move to 6.2.3. so we have to 3.2.3, I'm sorry. So the question says distance between the hot air balloon and stone B at the instant when stone A strikes the ground. So stone A strikes the ground at t equals to 6,6983 seconds, and then stone B is dropped 5 seconds later after stone A is dropped. So at this instant, stone A has traveled 6.6985 minus 5, right? Which will be delta t of stone B equals to 1.6985 seconds, right? So this is delta t of stone B, right? This is the time delta B had spent in motion, where stone B, this is the time stone B had spent in motion when stone A struck the ground. So we're supposed to find the distance between the hot air balloon and stone B. So the hot air balloon, we know that it is moving at a constant speed, right? So to calculate that distance, we know that VI equals to 2.9635, and then we know that VF is also 2.9635, and we know that acceleration equals to 0, and we know that delta t equals to 1.6985 seconds, right? And then what we are interested in finding is delta y. So which equation can we use to find delta y? I think we can use quite a few. So we can use delta y equals to vi delta t plus 1 over 2 a delta t squared. So we know that the acceleration is equal to 0, right? So this part of the equation is gonna fall off. So we're gonna get delta y equals to vi delta t, which is equals to 2.9635 multiplied by 1.6985, which is gonna give me, let me put that in my calculator. So we have 2.9635 multiplied by 1.6985, which gives me 5.0335 meters, right? And then now this is delta y for our stone B, right? So this is delta y for our balloon, and then now for stone B, we know that vi equals to 2.9635. We know that acceleration is minus 9.8 meters per second squared. We know that delta t is equals to 1.6985 seconds, and I think this is all we know for stone B. So the only formula we can use to find delta y with this information is delta y equals to vi delta t plus 1 over 2 a delta t squared, right? So what is vi? Vi is 2.9635, and then delta t is 1.6985, and then plus 1 over 2, a is minus 9.8, delta t again is 1.6985, but now squaring, which is equals to, let me put that in my calculator real quick, 2.9635 multiplied by 1.6985 plus 1 over 2 multiplied by minus 9.8, multiplied by 1.6985 squared. That gives me minus 9.1114 meters, right? So now the distance in between is gonna be equals to 5.033 plus 9.1114, which is 5.033 plus 9.1114, which is giving me 14.14 meters. So when you add them, you have to reject the signs, because if you pay attention, if you just add them with their signs, then you're not gonna get the distance in between. 3.3 says on the same set of axes, draw position time graphs for both the hot air balloon and stone A from the moment the stone is dropped until it strikes the ground. Use the ground as zero reference. Label your graphs balloon A, balloon and A being the stone, right? So 3.3, this is my ruler, my x-axis. So let's say this is 200 meters where stone A is dropped, right? And then what happens to the balloon? The balloon keeps going up at constant velocity, right? So here we're gonna have our graph for the balloon, which we are told we should label balloon. And then what happens to the stone? The stone goes up for some time before it starts going down, right? Because this V initial is 2.9 meters per second, so it will go up for that short amount of time, and then eventually it will go down, and then it strikes the ground. So this is our time on our x-axis, and then on the y-axis is our y in meters. So what we have below is a velocity time graph that shows the motion of a ball thrown vertically downwards, right, from the top of a building and bouncing off the floor as it hits the ground. And then we can ignore the effects of air friction, and then it's a must that we take upward as positive. And then the first question, 3.1.1, says using equations of motion only, let's calculate the height from which the ball is thrown, right? So we are looking for delta y, the height at which the ball is thrown. Problem solving 101. We'll look at the information we have, right, and try use that information to find out what we don't have, right? So what information do we have here? At t is equals to 0, we have a velocity here of which the ball is thrown at, right? So the velocity that we have here, which will be our VI, right, is given as minus 20 meters per second. And then when the ball hits the ground, it has a velocity of minus 25 meters per second, right? So we can say our VF in this instance would be minus 25 meters per second, right? We know acceleration. We always know it's a constant, right? If we're taking upward as positive, then our acceleration should be minus 9.8 meters per second squared. So we have VI, we have VF, we have our acceleration, and we'll need delta y, right? So which equation of motion has these four variables that we can use? We know fully well that that equation is VF squared is equals to VI squared plus 2a delta y. We have the acceleration, we have VI, we have VF. We're looking for delta y, right? So what is VF? VF is minus 25, right? That's the velocity at which our object strikes the ground. And then VI is minus 20, the velocity at which it is thrown off the building, right? Plus 2 multiplied by A. A is our gravitational acceleration, minus 9.8, right? And then we're looking for delta Y. So basically, the physics is done now. We are just solving the math. So we're going to have minus 25 squared minus 20 squared being equals to 2 multiplied by minus 9.8 delta Y. We just took minus 20 squared to the left hand side, right? So now it will be obvious what we're going to do. We're going to divide both sides by 2 multiplied by minus 9.8. So if we do that, we're going to get delta Y being equals to minus 25 squared minus 20 squared, everything divided by 2 multiplied by minus 9.8, and then our delta Y is equals to minus 11.48, right? Which is just 11.48 meters. So the height above the ground is 11.48 meters. Now we can do 3.1.2. 3.1.2 says let's find the time t on the graph. So time t on the graph is here, right? So let's analyze our motion. Here at this point, the object is thrown downwards, right? And then at minus 25, it hits the ground. When it hits the ground, it bounces off with a velocity of 12 meters per second, right? Until it reaches its maximum height. So what we do here, we calculate the time for this part of the motion from the moment it is thrown downwards to the moment it hits the ground. And after we're done with that, we calculate the time from the moment it leaves the ground to the maximum height which it reaches, right, when its velocity is equal to 0. So for that part of the motion, we have VF, obviously, right? And then we have VI, we have A, but then now we don't need delta Y. We already have it. We're looking for delta T, right? We want that time because that time, delta T in our graph here is the time from the instance the ball or the object is thrown downwards, right? So here for that first part of the motion, we're gonna get VF is equals to VI plus A multiplied by delta T. What is VF? Minus 25. And what is VI? Minus 20. We know fully well what our acceleration is, minus 9.8, and then multiplied by delta T. So we're gonna have minus 25 minus 20 being equals to minus 9.8 multiplied by delta T. So we divide both sides by 9.8, right? If you do that, you get delta T being equals to 0.5102 second, right? And then we are done with that part of the motion. Now we need the part of the motion from the time it leaves the ground to the time it reaches its maximum height, right? So what do we have there? We have VI for that part of the motion, and then we have VF, right? Maximum height. We know the velocity is equal to 0, and then we have the acceleration, and we're looking for the time. So what is VF in that instance? We're still using the same formula. VF is equals to VI plus A delta T. So VF is 0, right? Maximum height, and then VI will be 12. Here it is, right? 12 meters per second, and it's positive because the object has left the ground. It is now moving up, plus the acceleration, which is minus 9.8 multiplied by delta T. So you can see what we're gonna do here. We're gonna take 12 to the left hand side and divide both sides by 9.8. So delta T is going to be equals to minus 12 divided by minus 9.8, right? And that will be equals to 1.2245 seconds, right? So now that time on our graph will be equals to the time from here to here, right? Which is 0.51, and the time from here to here, which is 1.2245. So we add in the 2, we have 0.51 plus 1.2245, right? And that should be equals to 1.7345 seconds. 3.1.3, which says that let's determine using equations of motion the magnitude of the displacement of the ball from the moment it is thrown until time t. So the ball is at some height, right? And then it is thrown downwards, and then it hits the ground. After it hits the ground, obviously it's gonna move up, right? And then it moves up to some maximum height. At the maximum height, that's our time t. At this instance, we know the height the ball was thrown above the ground, but we're looking for the displacement of the ball, the change in position from the time it is thrown until it reaches maximum height. This is the object's maximum height after it bounces off the ground, right? So we're basically looking for this part here. This is the part we're looking for. So if we find this height from the ground to its maximum height, then we're going to be able to calculate that displacement that we are looking for. So what are we saying? We know the height, right? We know fully well that the height is at 11.48 meters above the ground, right? Now let's find the maximum height it reaches after the bounce, right? So we know fully well that the VI that it leaves the ground with is 12 meters per second, and then the VF, because it's at maximum height, it's 0, right? And then we know the acceleration, but now we're looking for delta y and not delta t. So which equation of motion can we use? We're going to use VF squared is equals to VI squared plus 2a delta y. So VF squared, we have 0 squared, which is equals to VI squared. So that's 12 squared plus 2 multiplied by minus 9.8 delta y. It should be obvious. We're going to take 12 squared to the left hand side and divide both sides by this coefficient here. If we do that, we're going to get delta y being equals to minus 12 squared divided by 2 multiplied by 9.8. This here is supposed to be a minus, and then the answer we get in is 7.346 meters, right? So now our displacement will be equals to 11.48 minus 7.3469, which is equals to 4.1331 meters, right? Now we can move to 3.2. So 3.2 says, can you sketch a position versus time graph for the motion of the ball from the moment it is thrown until it reaches its maximum height from the bounce? Use the ground as the 0 position, right? And then we must indicate the height of which the ball is thrown and the time t, right? Which is things we have calculated. So let me just sketch our Cartesian plane. So on the x-axis we have the time in second. So on the y-axis we need delta y in meters, right? So let's start by indicating the maximum height which it is thrown, right? So the maximum height we say is 11.48. Yeah, like we've been saying, we're moving from maximum height and then it is thrown downwards, right? And then it hits the ground, and then it bounces until it reaches its new maximum height, right? This height here, we know fully well what it is, 7.3469, and then the time here, which is the time t that we're supposed to indicate, we just calculated it not long ago, right? 1.73 second.